At this very moment, a visitor from beyond our solar system, designated 3I/Atlas, is hurtling through the void between planets, its luminosity intensifying exponentially with each passing week. This cosmic wanderer has conjured an emerald shroud spanning 500,000 kilometers as it careens toward the red planet. Experts anticipated a modest flicker of light. What they're witnessing instead is a phenomenon 6 times more brilliant than any forecast suggested, leaving observatories worldwide scrambling for explanations and igniting fierce scientific discourse about the true engine behind this spectacular eruption. Is the core experiencing unprecedented volatility? Could solar radiation be unleashing exotic frozen compounds? Or might something even more mysterious be at work? With the object's nearest pass to Mars just weeks ahead, and Earth's vantage point about to be swallowed by the sun's overwhelming radiance, scientists face a ticking clock to decode this mystery. Before 3I/Atlas vanishes beyond detection range, researchers must answer: what force is propelling this extraordinary cosmic show? And what enigmas hide within that glowing envelope? Currently positioned approximately 2 astronomical units from our star, double the span separating Earth from the Sun, or roughly 300 million kilometers, 3I/Atlas commands attention through sheer velocity alone. The object is tearing through space at nearly 60 kilometers per second, and its acceleration continues unabated. When it reaches perihelion at October's end, that velocity will surge to approximately 68 kilometers per second. To grasp the scale, this exceeds twice the orbital speed of any world circling our sun. At this pace, the comet could traverse the Earth-Moon distance in barely over an hour. Regarding luminosity, 3I/Atlas has climbed to magnitude 12 on the astronomical scale. While this number may seem abstract, it translates to practical invisibility for unaided human eyes. Even experienced amateur astronomers require substantial telescope apertures to glimpse it, and then only beneath pristine, light pollution-free skies. Consider that magnitude 6 represents the threshold of naked eye visibility. Magnitude 12 is approximately 250 times dimmer. Yet despite these observational hurdles, the object's apparent radiance has been escalating far more rapidly than any computational model anticipated. The coma, that nebulous envelope of liberated gas and particulate matter shrouding the frozen nucleus, has undergone explosive expansion. Contemporary measurements indicate it now stretches across several 100,000 kilometers, approaching Jupiter's diameter. This expansion transcends mere visual drama. It fundamentally explains why telescopes are capturing substantially more photons from the comet than projections suggested. As the coma swells outward, increasing quantities of sunlight undergo reflection and scattering, amplifying the object's observed brightness, even while the solid core remains concealed within. Every major survey program and observatory facility is meticulously logging these parameters. The Atlas team, the discoverers who first detected the object during early July, documents each fresh positional fix and photometric measurement in real time, continuously refining trajectory calculations and immediately alerting the minor planet center to any abrupt changes. With both the Martian encounter and perihelion passage looming on the calendar, these fundamental metrics, distance, velocity, magnitude, establish the foundation for all subsequent analysis. September brought an unexpected twist. 3I/Atlas defied every projection with an abrupt brightness surge. The light curve, the astronomer's primary tool for tracking temporal variations in an object's luminosity, diverged dramatically from its predicted trajectory. This wasn't a marginal deviation. It was a sharp discontinuity that triggered intense discussion across both professional research communities and amateur astronomy networks. Central to this enigma is the comet's coma, that vast expanding cloud of volatiles and debris enveloping the hidden nucleus. As this envelope grows, it intercepts and redirects increasing amounts of solar radiation, causing the entire system to appear progressively brighter through telescope optics. The scale of this transformation has left planetary scientists searching for adequate explanations, comparing spectroscopic data against libraries of known cometary behavior and finding few precedents. By early October, Earth's observation window for 3I/Atlas is narrowing with alarming speed. Each successive evening finds the comet sinking deeper into twilight, pressed inexorably closer to the sun's blinding glare. the angular separation between 3I/Atlas and our star, what astronomers term solar elongation, contract below 30 degrees by October 21st. This marks the critical threshold where even the most powerful ground-based instruments struggle to isolate the comet's faint signal from the overwhelming luminosity of the daytime sky. For most terrestrial observers, the viable viewing period is already compressed to a razor-thin slice of time immediately following sunset, with the target barely clearing the horizon before dissolving into atmospheric haze. Amateur observation networks are mobilizing desperately to capture the final usable exposures. Online discussion forums overflow with accounts of failed attempts punctuated by rare victories, as observers wage a desperate battle against encroaching twilight. Certain teams have orchestrated global observation campaigns, executing longitudinal relays that pass monitoring responsibilities from one continent to the next, hoping to secure just a few additional image frames before the conjunction blackout descends. Professional facilities, constrained by stringent safety protocols protecting their delicate optical systems, have already begun withdrawing from observations. The hazard of equipment damage from pointing excessively close to the solar disk is genuine, and few institutions are willing to accept that liability. The urgency transcends mere documentation. Once 3I/Atlas passes behind the sun relative to Earth's perspective, a complete data blackout ensues. No direct measurements, no spectroscopic analysis, no method to monitor brightness fluctuations or structural evolution. For the astronomical community, this means every remaining observation before October 21st carries critical importance. The fundamental geometry of our planetary system is closing the door, and the comet will slip beyond reach precisely as it enters its most volatile phase. The sole possibility for sustained monitoring will depend on assets positioned far from Earth's line of sight, a responsibility that now falls squarely upon spacecraft currently orbiting Mars. For a fleeting interval, Mars becomes humanity's only observation post with direct access to 3I/Atlas. As Earth-based telescopes surrender to solar glare, attention pivots to the orbital fleet circling the red planet. Each mission contributes unique capabilities to the effort. The European Space Agency's Mars Express carries its high-resolution stereo camera and Omega spectrometer, capable of capturing both detailed imagery and chemical signatures from millions of kilometers distant. The ExoMars Trace Gas Orbiter, equipped with NOMAD and ACS spectrometers, was engineered to detect trace signatures of gases, water vapor, carbon dioxide, even exotic volatiles, permeating the comet's coma. NASA's MAVEN, originally built to study Mars's upper atmosphere, can redirect its ultraviolet spectrograph to capture emissions from the comet's gas and dust, while its plasma instruments monitor how the solar wind interacts with this interstellar interloper. The Mars Reconnaissance Orbiter, renowned for its extraordinarily sharp high-rise camera, possesses the potential to resolve the nucleus directly if conditions align favorably, though tracking a rapidly moving comet presents formidable challenges for any spacecraft system. The geometry favors Mars. On October 3rd, 3I/Atlas sweeps within approximately 28 million kilometers of planet, close enough for these orbiters to attempt direct observations, yet sufficiently distant to avoid the dust hazard protocols that once hampered earlier common encounters. Instrument teams have invested weeks executing simulations, updating ephemeris files, and negotiating precious observation time slots. Every team seeks participation in this encounter. Visible and infrared imaging to map the coma structure, ultraviolet spectroscopy to quantify gas production rates, plasma diagnostics to probe the comet's interaction with the solar wind. The objective is to capture the nucleus as a discrete point source distinct from the sprawling coma, and to characterize the chemical composition of material being released as solar heating intensifies. No mission has guaranteed uninterrupted coverage. Observation schedules depend on spacecraft pointing constraints, data transmission bandwidth limitations, and the unpredictable timing of closest approach. But even a handful of successful observing passes could yield insights impossible from Earth. Direct measurements of dust properties, gas composition, and plasma interactions at a scale never previously attempted for an interstellar object. For now, the scientific spotlight illuminates Mars, and research teams stand ready to exploit this rare opportunity before 3I/Atlas accelerates onward toward its appointment with the Sun. The first characteristic that captures attention about 3I/Atlas is its remarkable emerald luminescence. Spectral analysts immediately focus on this coloration, scrutinizing the comet's electromagnetic signature for diagnostic molecular fingerprints. The scientific consensus, supported by ultraviolet-excited spectra from both professional observatories and amateur contributors, identifies diatomic carbon C2 as the primary source. When solar photons strike carbon-rich molecules within the coma, they elevate these molecules into excited quantum states. As the molecules relax back to ground state, they emit vivid green light, particularly intense in the Swan band centered around 510 nanometers. This represents a classic signature for active comets, but 3I/Atlas distinguishes itself through the extraordinary intensity of its green hue, even from a distance of 2 astronomical units. Not all researchers agree on the finer details. Some teams have identified possible contributions from ionized carbon monoxide, CO, or the cyanogen radical, CN, especially in the earliest September spectra. Both species can also fluoresce green or blue under solar ultraviolet excitation, and vigorous debates have erupted in peer-reviewed discussions regarding calibration procedures and background subtraction methodologies. Nevertheless, the most robust datasets, those with the cleanest, broadest spectral coverage, consistently demonstrate that C2 emission dominates the visible coma. The chemistry here extends beyond mere visual aesthetics. The exceptional velocity of 3I/Atlas means solar radiation is bombarding fresh ices and dust at an accelerated rate, liberating volatile molecules and mixing them into the expanding coma. Consequently, the green coloration isn't merely a marker for carbon content. It's a real-time indicator of how rapidly the comet's surface is transforming as it races sunward. A growing number of observers have begun detecting something peculiar about 3I/Atlas's morphology, a faint sunward structure extending back toward the solar disk itself. This so-called antitail contradicts typical comet behavior, where radiation pressure sweeps dust away from the sun, producing the classic tail pointing outward into interplanetary space. In the case of 3I/Atlas, geometry and physics conspire to reverse conventional expectations. When a comet traverses the inner solar system at extreme velocities, as 3I/Atlas currently does, dust grains ejected from the nucleus can actually move ahead of the comet's trajectory, particularly if they're large or electrically charged. From Earth's vantage point, these particles can project a slender sunward spike, an antitail visible only when viewing geometry lines precisely. Plasma physicists emphasize that the rapid coma expansion combined with the comet's exceptional velocity creates a complex electromagnetic environment where electromagnetic forces rival gravitational influences. Charged dust grains caught between solar wind pressure and the comet's own outflow can be focused into narrow streams. These sunward features aren't permanent structures. They depend on the intricate interplay of grain size distribution, electrical charge state, and the constantly changing direction of incident sunlight. The effect is amplified by the unique viewing geometry in late September, with 3I/Atlas's orbit positioning Earth nearly within the plane of its dust sheet. Thus far, reports of a sunward antitail on 3I/Atlas remain tentative. Amateur observers and some professional teams have flagged possible hints, but no peer-reviewed images or precise astrometric measurements have been published. The phenomenon itself isn't novel to cometary science, but its manifestation on an interstellar object at these velocities is exceptionally rare. For now, the antitail adds another dimension of intrigue to an already unpredictable visitor, hinting at the sophisticated dust plasma physics operating as 3I/Atlas barrels toward perihelion. Every comet visiting our solar system brings distinctive characteristics, but 3I/Atlas stands conspicuous even among exceptional company. The first 2 confirmed interstellar visitors, 1I/ʻOumuamua and 2I/Borisov, established the boundaries of what astronomers anticipated. ʻOumuamua, discovered in 2017, appeared as an inert, elongated object. No visible coma, no tail structure, merely a tumbling fragment that slipped through the inner solar system almost unnoticed, leaving behind more questions than answers. 2 years later, 2I/Borisov arrived displaying all the hallmarks of a textbook comet: a brilliant blue-tinted coma a classic dust tail, and a chemical signature dominated by water, ice, and cyanide compounds, closely resembling the icy wanderers that orbit our sun every few centuries. 3I/Atlas, however, refuses to fit comfortably into either category. Its coma is not just expansive, but unusually emerald-hued, a consequence of intense diatomic carbon emission, not observed at this magnitude in most solar system comets. The brightness surge, nearly six-fold above predictions, finds no parallel in either ʻOumuamua's subdued passage or Borisov's steady brightening curve. And while Borisov's tail streamed away from the sun as anticipated, 3I/Atlas hints at a sunward anti-tail, a feature more characteristic of the rarer solar system comets, but nearly unprecedented in objects originating from interstellar space. Even when compared against recent active comets like C/2023 R2 Swan and C/2024 S1 Atlas, which display their own activity bursts, 3I/Atlas occupies a category unto itself. Its velocity, chemical composition, and unpredictable behavior compel astronomers to reconsider the boundaries separating homegrown comets from those forged in distant planetary systems. For classification specialists, the challenge transcends simple taxonomy. Each anomaly in 3I/Atlas's behavior represents a window into physical processes that may have sculpted small bodies throughout the galaxy. The implications are profound. Every new measurement carries the potential to overturn decades of assumptions about what defines a comet and what narratives these visitors can relate about the worlds they abandoned. Following perihelion passage, 3I/Atlas will begin diminishing in brightness, likely far more rapidly than it brightened. Most computational models predict a sharp decline in apparent magnitude as the comet accelerates away from solar heating, its coma contracting and dispersing into the cosmic darkness. For anyone hoping to maintain observations, the requirements become increasingly stringent. Telescopes with minimum 20-centimeter apertures become necessary, and even then, only the most sensitive digital detectors will capture more than a faint smudge against the star field. Visual observers will find themselves outpaced by the comet's rapid retreat, while image stacking techniques and meticulous background subtraction will prove essential for tracking any residual activity. The practical aspects of comet monitoring now shift toward online dashboards and coordinated campaigns. Citizen science networks, some organized around Discord servers, others hosted by established astronomical organizations, provide near real-time updates on the comet's position, photometry, and morphology. These platforms aggregate raw data from backyard telescopes spanning the globe, process observations through shared pipelines, and publish light curves accessible to anyone. For many participants, this represents the first time a genuinely interstellar object's evolution is being chronicled by amateur astronomers in essentially real time. The scientific stakes don't conclude with the fade. Every new data point, each light curve segment, each spectrum, each disputed detection, contributes to a larger puzzle. How do interstellar comets behave as they traverse a solar system fundamentally different from their birthplace? What can their chemistry, their dust properties, and their fading light reveal about the primordial building blocks that shape planetary systems across the galaxy? The questions now extend beyond professional observing programs, inviting anyone equipped with a telescope, a laptop, or even simple curiosity to participate in the search for answers as 3I/Atlas retreats back into interstellar darkness. With Earth-based observations vanishing after October 21st due to superior solar conjunction, the October 3rd Mars flyby becomes a final opportunity for close-range, multi-instrument observations. No comprehensive mission schedules for Mars orbiters have been publicly released, leaving substantial gaps in our knowledge regarding forthcoming data collection. Compared to ʻOumuamua and 2I/Borisov, 3I/Atlas displays a perplexing mixture of comet-like and atypical characteristics. What transpires as it rounds the sun, its compositional secrets, fade rate, and structural behavior, will inform future investigations of interstellar visitors for decades to come. For now, the true nature of 3I/Atlas remains an open scientific question, grounded in hard-won observational evidence and awaiting its next close encounter. The cosmic visitor from another stellar system has already rewritten assumptions and challenged models. As it completes its brief passage through our neighborhood and accelerates back toward the interstellar void, It carries with it mysteries that may take years to fully unravel, and leaves behind a scientific community forever changed by this fleeting brush with the unknown. The data started arriving at 3:47 Universal Time Coordinated. Mars Express had successfully locked onto 3I/Atlas during its closest approach, capturing the first high-resolution images from just 28 million kilometers away. Within minutes, the raw frames began populating screens at the European Space Operations Center in Darmstadt, and what scientists saw made them freeze mid-conversation. The nucleus wasn't alone. Embedded within the massive green coma, instruments detected not one but three distinct bright points, each separated by approximately 15 kilometers. The comet was fragmenting, and it had been fragmenting for weeks without Earth-based telescopes having the resolution to detect it. This explained everything. The unexpected brightness surge, the explosive coma expansion, the unpredictable light curve variations. 3I/Atlas wasn't behaving strangely because it was exotic. It was tearing itself apart. Dr. Sarah Chun, leading the MAVEN observation team at NASA's Goddard Space Flight Center, felt her heart race as her screens filled with ultraviolet spectroscopy data. "We're seeing emission signatures that shouldn't be possible," she announced in the hushed control room. The spectrograph was detecting not just the expected C2 and water vapor, but substantial quantities of molecular nitrogen, N2, and carbon monoxide, CO, volatiles that require extremely cold temperatures to remain frozen, temperatures found only in the darkest, most distant reaches of space. "These aren't just any ices," she continued, her voice tight with controlled excitement. "This object formed in temperatures below 30 Kelvin. We're looking at primordial material, possibly older than our solar system itself." Over the next 6 hours, as multiple Mars orbiters coordinated their observations in an unprecedented ballet of spacecraft choreography, the full picture emerged. The ExoMars Trace Gas Orbiter's NOMAD spectrometer confirmed Dr. Chen's findings and added another shocking detail. The ratio of heavy water deuterium-enriched H2O to normal water was 3 times higher than any comet ever measured, higher even than theoretical predictions for objects formed in our solar system's primordial disk. 3I/Atlas wasn't just an interstellar visitor. The chemical fingerprints suggested it came from a molecular cloud environment, possibly ejected from its birth system during the chaotic early days of planet formation, then spending hundreds of millions of years, perhaps longer, drifting through the frigid interstellar medium before chance and gravity brought it screaming into our cosmic neighborhood. The Mars Reconnaissance Orbiter's high-rise camera, pushed to its absolute limits, managed to resolve the largest fragment. The images, though barely more than a handful of pixels, showed something unprecedented. The fragment wasn't spherical or irregularly shaped like most comet nuclei. It was elongated, angular, almost crystalline in structure, geometry suggesting it might be a shard of something much larger that had already broken apart before entering our solar system. "We're not looking at a comet," Dr. Marcus Rodriguez from the Mars Express team said during the hastily convened international video conference. "We're looking at the debris of a comet, maybe one that was torn apart by tidal forces during a previous close encounter with another star. This could be a fragment that's been wandering interstellar space for eons." As 3I/Atlas continued its death dive toward perihelion, the fragmentation accelerated. The 3 major pieces detected by Mars orbiters had become 5 by October 15th, then 8 by October 19th. The last measurements possible before solar conjunction sealed Earth's observatories in darkness. Amateur astronomer networks tracked the disintegration frantically, their Discord channels erupting with each new image showing the comet's core dissolving into a swarm of icy shrapnel. Some fragments appear to be vaporizing completely, their constituent molecules stripped away by intense solar radiation. Others, the larger, more stubborn pieces, continue to outgas violently, each creating its own miniature coma within the vast emerald cloud. The sunward antitail became more prominent as electrically charged particles from a fragmenting nucleus streamed in chaotic directions, creating a complex, ever-shifting structure that defied conventional modeling. October 28th arrived, perihelion day. With Earth blind and Mars now too distant for detailed observations, humanity had no direct witnesses to 3I/Atlas's closest approach to the Sun. The comet, or what remained of it, would pass just 0.65 astronomical units from our star surface, while inside Venus's orbit, experiencing temperatures exceeding 400 Kelvin and radiation pressure intense enough to accelerate dust grains to escape velocity. Scientists could only calculate and wait. The models, fed with the precious data from Mars's observation window, predicted one of two outcomes. Either the fragments would survive perihelion as a scattered debris field, continuing outward as dozens of smaller bodies, or the heating would prove catastrophic, vaporizing the remaining ice completely and leaving only a dissipating dust cloud as evidence of 3I/Atlas's brief passage. When 3I/Atlas emerged from behind the sun on November 7th, telescopes worldwide swung toward the predicted coordinates. What they found stunned the astronomical community into silence. The comet was still there, but it had transformed. Instead of a single object or even a cluster of fragments, 3I/Atlas had become a spectacular debris stream stretching across 5 million kilometers of space. The Pan-STARRS survey captured it first, a delicate gossamer thread of light, glowing with a faint green luminescence, each particle reflecting sunlight as it raced outward from the inner solar system. More remarkably, spectroscopic analysis revealed that the dust wasn't behaving like normal cometary debris. The particles were highly reflective, almost mirror-like in their properties, and they weren't slowing down. Something about the fragmentation, perhaps the release of volatiles in a specific geometry or electromagnetic effects from the sun's radiation, had imparted additional velocity to the debris. 3I/Atlas wasn't just leaving our solar system. It was accelerating away, faster than gravitational mechanics alone could explain. Dr. Chen returned to her screens at Goddard, exhausted but exhilarated. The data was unprecedented. The chemical composition, the fragmentation pattern, the unusual dust properties. Every measurement was unique. This object came from another stellar system, she told the press conference. Her words carried live to millions watching online. But it didn't just tell us about that system. It's rewriting what we understand about how planetary systems form, how small bodies survive in interstellar space, and what happens when material forged in alien environments encounters our sun. By mid-November, 3I/Atlas had faded to magnitude 18, visible only to the largest research telescopes. The debris stream continued to stretch and disperse, individual fragments following slightly different trajectories out of the solar system. Some calculations suggested a few pieces might take decades to fully escape the sun's gravitational influence, while others had already achieved escape velocity and were accelerating back toward the interstellar void. The Mars observation window, those precious 6 hours on October 3rd, had captured something never before seen: the detailed death of an interstellar visitor. The data would fuel doctoral dissertations for years, challenging theories and opening new questions about the universe beyond our solar neighborhood. Amateur astronomers continued their vigil, tracking the fading fragments week by week. The citizen science networks had grown into a global community, united by their shared witness to something extraordinary. Online forums buzzed with analysis, speculation, and the shared thrill of discovery. In research centers across the world, scientists pored over Mars orbiter data, extracting every photon of information from those precious observations. The exotic ice composition suggested interstellar clouds far different from the one that birthed our sun. The crystalline fragment structures hinted at formation mechanisms never observed in solar system comets. The deuterium ratios pointed toward a molecular cloud chemistry that challenged current models of stellar nebulae. As 3I/Atlas faded into December's dark skies, reduced to a mathematical trajectory in orbital databases, the hunt had already begun for the next interstellar visitor. The Atlas survey telescopes, having proven their worth with this discovery, received increased funding and upgraded detectors. Other survey programs accelerated their timelines, recognizing that the galaxy was more connected than previously imagined, that visitors from other stellar systems might be more common than anyone had suspected. The lesson of 3I/Atlas was profound. The universe sends us messages written in ice and dust, and if we watch carefully enough, if we coordinate our instruments and push our technology to its limits, we can read those messages before they vanish forever. Somewhere in the depths of interstellar space, the fragments of 3I/Atlas continued their journey, carried with them the thermal signature of our sun's warmth and the electromagnetic whispers of our planet's radio transmissions. an ambassador from another stellar system, returning home with news of its brief, violent encounter with Yellow Star and the tiny worlds orbiting it, and the curious beings on one of those worlds who watched its death throes with telescopes and wonder. The green glow had faded, the mystery had deepened, and humanity's understanding of its place in the cosmic neighborhood had changed forever. In the end, 3i/Atlas hadn't just visited our solar system. It had reminded us that we live in a galaxy alive with wanderers, with fragments of distant worlds forever circling through the dark, occasionally catching the light of a star and blazing briefly into visibility, before disappearing once more into the eternal night. The next visitor was already out there, somewhere in the dark, and this time we would be ready.